Let's take a look at our first example here. Now, reactions in kinetics or reactions under kinetics have to do with the rate of reaction and the speed of the reaction. So, a lot of you will like this because it's very similar to physics. We also have the time factor here is going to be part of the overall equation that we're looking at. Now in physics, you were doing lots of like distance over time kind of thing, which is what, velocity, I think, if I remember the little bit of physics I tried to learn last year to help my son. But here, we're not going to be dealing with distances or other variables. We're going to be looking at concentrations. So here, we're going to assume this is a 1 liter vessel, okay? And we have a very basic reaction going on where we have, you know, A going to B here, like so. A going to B. Reactant A changing over into reactant B. Now, that means this is a molarity of 1 to start with of all reactant A. And as you'll see as we progress over time, 20-second mark, the middle vessel here, some of the reactant has changed over and has now become product. So we have B in here. What you should be noting is the numbers though. The amount of B that has been formed from the reaction is also actually the same amount that has disappeared for A. So that's what you should note here. And so basically the change here was 0.46. And at the 40-second mark over here, looking at how much has changed from the 0.54 to the 0.3, that's a difference of 0.24 molar has changed, where it has disappeared from A and then formed that same amount in B. But noticing that pattern here at the 0 seconds to the 20 seconds to the 40 seconds, what is happening to our reaction rate as time goes on? What's happening to the reaction rate, the speed of the reaction? It is slowing down. As you see, the changeover is becoming less, the change in the concentration as we go on. Now, thinking about collision theory, okay, can we come up with some reasons as to why the reaction is going to slow down as time goes on? Yes, we have less of our reactants, right? And if we're thinking of our collision theory, particles have to collide. They have to collide with enough energy and with the right orientation. But if they're not bumping into things to react, you know, say they bump into the B's, well, they're not going to react with the B part, so you have less reactants. So that's going to change the amount of products that can be made because the collisions of our course are not going to be taking place at such a high amount as they were initially at the beginning of the reaction. So reactions are going to slow down. They're going to start off faster in the beginning and decrease in rate as you go down or as you continue on with the time. So what is a reaction rate? It's the change in concentration of a reactant or product per unit time. Now, rate laws and kinetics focus mainly on reactant changing. That's what we're really paying attention to here because that's the measurable part of how they collect the experimental data. So we're changing concentration over time. and mainly focusing on the reactant, although technically I guess you could look at the products, but they just typically gather data about the about the reactants. Now a lot to absorb here on this slide. Average reaction rate is basically this formula right here. It's the change in concentration over the change in time. But realizing if we're referring back to our original diagram, our original reaction of A changing over to B, the rate of disappearance of A, the reactant, would equal the rate of the appearance it would actually equal the rate of the appearance of the product here. And that is because we saw in the data the amount that disappeared was the amount that appeared, and so forth. Rates are always going to be expressed as positive quantities. So we know that the ones that are disappearing, like A here, if you're actually calculating it, you're doing 2 concentration points and 2 time points. They factor in the negative in front, because if you're disappearing, your final concentration at your time is going to be less than your initial concentration, so that top numerator number will always be negative. But they factor it into the equation for you, so you will get a positive rate, as shown here. Now, B, of course, is appearing, so you don't have that problem, because the numerator, the top part here, that change in concentration will always be a positive value, because the amount of concentration at the time 2 is going to always be higher than the amount that it was at time 1. And you can go any time interval. You can calculate the average rate at any time interval. Don't forget bracket notation. You're going to see it all throughout this unit. Bracket notation means concentration. Okay? Concentration is moles over liter. You're going to see everything, all the chemical species in brackets. You just automatically need to think molarity. All right? So this is the general idea of working with reaction rate. Now you're also going to see data tables in kinetics, lots of data tables. This one happens to be the decomposition of nitrogen dioxide, where we have the time interval in seconds here, okay? We have the concentration of the NO2, concentration of the NO, and the concentration of the oxygen here. So I want you to take a moment, look at the questions and the notes, and also look at the data, analyze it, examine it, and then we'll talk about it in just a second. Okay, so how would the rate of disappearance of a reactant change over time? You know, like in this reaction right here, what are we seeing in terms of the reactant? Slow down or decrease. All you have to do is kind of take a look at these numbers. This increment 0.0021, but down here 0.00004. So as you can see, the concentration changes is becoming less as you go through the time, and therefore that means it's slowing down. Definitely. How would the rate of formation of the product change as the reaction progresses? What are we noticing about those products? In this case, we have NO, nitrogen monoxide. We've got oxygen here. As the reaction progresses, what does the data tell us about the product formation and rate? It's also slowing down and decreasing. Very good. So you can see as we go along here and looking at these intervals, much wider interval initially towards the top at closer to times 0. and the concentration changes are becoming less as the reaction progresses. So it is slowing down from both aspects. Now the fun part, looking at it from, how about the rate of nitrogen monoxide to oxygen there? And you can calculate these. Does O2 decrease more than nitrogen monoxide? Yes, and that's what you should be noticing too, has something to do with the mole ratio in the equation. So for some of you, I'm going to write this out because it's not as, I would say, as easily seen. I'm one of the more math challenged for this particular unit, so I have to be very concrete and write out stuff to show the mathematical relationship, but some of you will just see it in your head, and I think that's wonderful because you're real math savvy. But if I'm looking at NO, and I want to do the change concentration of NO over the change in time to get that rate, like so. And just say, for this purpose, I'm going to do 0 to 200. All right? So if I'm doing 0 to 200, that's going to be, what, 0 point, oh, wrong one. I need NO. I'm in the wrong category here. NO is right here. 0.0052 minus the 0, starting at the top there, these two. And that's at 200 seconds minus 0. So what I get here for this particular rate, 2.6 times 10 to the minus 5 molar per second. That's the rate for the nitrogen monoxide. Now if I want to look at it and compare it to oxygen, I'm going to use that same interval, the 200 here. The change in concentration of oxygen over the change in time is going to give me my rate. So that's 0.0026 over the 200 minus 0. What you'll notice is this answer is 1.3 times 10 to the minus 5 molar per second. So if you're looking at the numbers, it should become evident to you that the NO is double the rate for that particular time interval than the oxygen. And I see that some people have already figured that out, that it's really based off of the moles in the balanced reaction. So the NO has a 2 in its mole ratio up there, and the oxygen is a 1. So the formation of nitrogen monoxide rate will be double that of the oxygen due to that stoichiometric relationship in the balanced reaction. Okay, does everybody see that? Like some people need to see this part, need to see the numbers, have it make sense. Others can just kind of visualize with the data. And if you do just look at increments here, like the 0.0066, this one, well, the oxygen's 0.0033. It is half. Most of these are virtually half, like 0.0021. Technically, I guess that would be like 10.5, but so it's 0.0011. It's close enough to be just about half. The mole ratio, the stoichiometric relationship in the balanced reaction definitely plays a role with the rate here. All right, now graphs. There's lots of graphs in kinetics too. So not only could you be given the data table like we just saw, here's the nice lovely graph. Some of you can't really see this very well, so I'm going to put this up here. The blue line is NO, the red line is O2, and the green line is NO2. Obviously, the NO2 is the reactant, so that's why we start here at the top. Okay, that one's going to be decreasing because it's disappearing. The NO and the oxygen start down here, and they're, my board is off a little bit, but it's increasing, okay, because the products are being formed. But what you should also notice about on the graph here is that molar relationship as well. 2NO2 gives you 2NO plus the 1 oxygen. Looking at their slopes, okay? Yes, I know the NO2 is decreasing and the other two are increasing, but if you look at their relative steepness of the slopes, the molar relationship should also be shown to you there. Because you can see the NO2 and NO are pretty much, even though they're going opposite directions, they have about the same steepness of slope, relating that 2 to 2 here. And the oxygen slope is definitely about half as steep as the other two, and that's because it has the 1 mole relationship there. So as you're going along, that's another aspect they like you to hone in on the graphs, because sometimes they'll give you the graph, but they won't necessarily give you the balanced reaction. So you should be able to tell kind of like, oh, that one looks double of that, or, you know, triple kind of thing. They're not going to give you anything that's going to be outrageous, but you see something like this without the balanced reaction, you should be able to tell that, yes, definitely the NO would be double the O2 in this particular case. So that brings us to the idea of those stoichiometric relationships within the balanced reaction. When it's not a 1-to-1 mole ratio, these are the different rate equations you would use. So go ahead and take a moment to write that down. They're factored in. Here's your coefficient for reactant A is the small a. That goes here. Remember, the reactants are disappearing. That's why you see this negative sign out front, making the rate overall positive. Then here, B is the coefficient of reactant B there, also disappearing. C being the coefficient here for the first product to be formed. And then last but not least, the D here. Okay, this is how you would write out in comparing the different rates to one another. So for example, let's go ahead and write out the comparable rates for our hydrogen iodide decomposing into hydrogen and iodine, separate elements. This one's disappearing, so, and since it has the 2 in front, it'll be -1/2. The change in the concentration of HI over the change of time, like so. That one being equivalent to the appearance of the okay, move over here please, thank you. The appearance of the hydrogen, which is just a 1 here, so we don't have to put 1/1 like that. You don't have to do that. And equivalent to our change in our concentration of I to the iodine appearing over the change in time. So these rates would all be equivalent. Noting that the hydrogen iodide is disappearing, the hydrogen is appearing, and the iodine is appearing, as we see. Okay, now we're going to look at these graphs and how to phrase these. So we're going to start off here. We're going to put all 3 lines on the graph, but first start off with hydrogen. Hydrogen, of course, is the concentration of hydrogen is decreasing as the reaction is progressing. This is the Haber process where you have a nitrogen plus hydrogen giving you ammonia. All right. So as it's progressing, the concentration of hydrogen is decreasing. As it's progressing, the concentration of nitrogen is also decreasing. However, they're not decreasing in the same amount. And we're going to compare the two. So they could give you a graph and then ask you a simple conceptual question like this. How does the rate of hydrogen compare in terms of nitrogen? Now some of you, like I said, very math savvy folks in here, I know that. You guys can just visualize and see it. I can't, so this is what I do. This will help the people that don't just see it in their head. I write out the rate equations and compare them. So if I'm putting it in terms of nitrogen, over here, that means the concentration of nitrogen is decreasing at 1/2 the rate of the hydrogen. I'm sorry, 1/3 of the rate of the hydrogen decreasing. Or you could say in terms of concentration of the nitrogen is disappearing at 1/3 the rate of the hydrogen disappearing. That is putting it in terms of the nitrogen. And typically what they do in the multiple choice problem is they're having you refer to it in terms of the nitrogen, but they'll also put the answer reversed where it would be referring to it in terms of hydrogen. Because hydrogen would be opposite. Like the concentration of the hydrogen disappearing would be 3 times that of the nitrogen disappearing. So make sure that you're referencing the right point so you select the correct answer there. So phrasing it, as the reaction progresses, the concentration of nitrogen decreases at 1/3 the rate of the concentration of hydrogen. Now let's look at the ammonia and compare the ammonia to the nitrogen. Here's our ammonia line, right? It's increasing, it's the product. It's kind of in between the slopes of the other two. So, as the reaction progresses, the concentration of ammonia is increasing. How does it compare to nitrogen? Let's put it in terms of nitrogen. And once again, a lot of you can just see that. Looking at your reaction, looking at the slopes. I need to look at the rate equations and compare them, and some of you can do that. So if I'm looking here, here's your nitrogen disappearing, here's your ammonia appearing, but since the ammonia has the two moles, that means the nitrogen concentration is disappearing. That rate is 1/2 the concentration of the ammonia appearing or increasing, whichever way you want to phrase it. So as the reaction progresses, the concentration of nitrogen decreases at 1/2 the rate that the concentration of ammonia increases. Like I said, the wording of these can be a little tricky, so do pay attention. And that's why sometimes I just have to scribble out the rate equations to make sure I'm referring to the right component at the right place. So now, well, the minus 1/2 is just telling you, well, in this case, it wouldn't be minus 1/2 because, I mean, you could say that ammonia is appearing at 2 times the rate of nitrogen disappearing, the concentration of nitrogen disappearing, that would be the other, if we were referring to it in terms of ammonia versus referring to it in terms of nitrogen. All right, so now let's take a look at comparing hydrogen to ammonia. Because now we have coefficients to deal with on both of those. Because hydrogen's a 3 for its coefficient and the ammonia is a 2. Now it's not really telling you which term to focus on. So let's look at it from both aspects. So let's look at it here. Here's the general equations. 1/2 times the rate of the ammonia, 1/3 times the rate of the hydrogen. So in this way, if you were phrasing it this way, you're referring to it in terms of ammonia. So the rate of the ammonia is, concentration is increasing. It's 2/3 times the rate of the hydrogen disappearing or decreasing. The concentration of that hydrogen disappearing or decreasing. That's if we're referring to it in terms of the ammonia. Now if we wanted to refer to it in terms of the hydrogen, you would go the other direction. As the reaction progresses, ammonia increases at 2/3 the rate that the hydrogen decreases. Here, other way, referring to it in terms of hydrogen disappearing. As the reaction progresses, hydrogen decreases at 3/2 the rate that the ammonia is increasing. So that hydrogen disappears, concentration of hydrogen disappears 3/2 the rate that the ammonia concentration is appearing. As long as everybody can see that, either by the mole relationships in the balanced reaction, by the slopes on the graph, and also by using the rate equations. You can use any of them, however you interpret it, whatever's the best way. All right, so now let's actually work with some numbers here and calculate the rate of decomposition of dinitrogen pentoxide, the reaction which creates nitrogen dioxide and oxygen, is 4.2 times 10 to the minus 7th molar per second. What is the rate of appearance of NO2 and O2? So go ahead, take a moment, try to calculate that out. Use those rate equations. Okay, let's take a look here. Now, like I said, probably already way ahead of me here, but this is what I would do. 1/2 the concentration and 205 for the change in time. I would write them out just so I have my reference point. Like so. Okay. Now we don't really have to worry about the negative here because it already gave us the rate, because we know the rate's positive. Okay, this value right here is the 4.2 times 10 to the minus 7 molar per second. So if I'm really comparing it and want to know what this one is, all I have to do is move the 4 over across, and I would have, 4/2 of the dinitrogen pentoxide is going to be equivalent to the nitrogen dioxide rate. So really 4 over 2 is really just 2 times. So 4.2 times 10 to the minus 7 molar per second, which is going to be 8.4 times 10 to the minus 7. Don't forget your unit, molar per second. Pretty easy. Now, the oxygen, okay, is basically just going to be 1/2 of that 4.2 times 10 to the minus 7. That gives you the change for the oxygen over the change in time there. So we end up with 2.1 times 10 to the minus 7 molar per second. I've seen these problems on pre-response questions where they'll refer to one specific reactant for you to calculate for based off of the information of the other ones. They might say experiment 2 or something like that. I don't believe so, but I wrote them out because, you know, some of us need the visual aid. For someone like you, though, I think you can probably get by with just maybe showing this part times that. I think that, yes, they would be able to give you the credit, although I will take a look at the scoring guidelines and see what kind of work they expect here to show, and I'll let you know. But that's a good question. All right, there we go. All right, instantaneous rate. It's just another thing you can calculate about the reaction. I don't think they really make you calculate instantaneous rate, but basically, I'm sure a lot of you, especially those taking calculus, really know what this is. On the graph, it's this point, and then they do the triangle there, and really, you're taking the derivative at that particular, it's that moment in time, period. Yeah, and then, of course, the instantaneous rate here, but what you notice, what's intriguing, as you can see, this is and this graph's hard to see. This is HI up here, and this is hydrogen down here, that curve. But as you can see, at that particular moment, that instantaneous rate, those are going to be the same value for both the appearing and disappearing. The disappearing of the reactant, which is HI, the appearing of the hydrogen. I'm sorry, in this case, the hydrogen's the reactant, so it's disappearing. The HI is appearing. But that's just showing you. It's the same formula, the change in the concentration over time, except for you're taking the derivative based off of the triangles there instead. Just another way, or another type of data point that you could calculate about a reaction. But most of the rate kind of problems are more like the previous problem, where they just give you a rate and expect you to calculate it based off the molar relationship. So there's a bigger, better picture, as you can see, showing that as well. You can do the time intervals, which is more like an average rate over that specific time interval. All right, types of rate laws. Now we're finally getting into rate laws. Nobody really has looked at rate laws because we don't teach this in Chem 1. There are two types of rate laws. And when we're saying write out a rate law, we're really talking differential rate laws. Differential rate laws care about two specific variables. They compare differential rate laws comparing the rate versus the concentration. Dependent on concentration. Rate dependent on concentration. So write out rate laws, we're talking rate versus concentration. That falls under the differential category, and also what we would call typically writing a rate law. The other one we're going to look at in part 2, which is called integrated rate laws. And integrated rate laws have a bunch of equations, and they have a bunch of data tables like those concentration versus time data tables. So this specific integrated part is going to be dependent on two variables as well. But those variables happen to be the concentration versus time. So rate versus concentration, concentration versus time. And they look different And the way that they're represented, like I said, integrated has its equations. Those equations are on the formula sheet. You'll be able to use that. There's a graphical analysis there that's slightly different. Differential rate law, we're going to really be looking at experimental data, writing out rate laws from experimental data, and from proposed mechanisms. That'll be part 3. All right, what does a rate law look like? All right, let's look at a particular one. We got the decomposition of nitrogen dioxide. How would we write out the rate law? Rate laws are always formatted in this particular, when you're writing out a rate law, it always follows this format. You write rate equals K, your concentration of your reactant, and then it's raised to a power, which is known as the order of the reactant. Now for this particular reaction, there is only the one reactant. So you would only see one reactant in the rate law. If it's a reaction that has more than one reactant, you might see 2 reactants in the rate law. There are concentrations in there. Always this format, rate equals K, bracket notation, concentration raised to a power, and that power is called the order of the reactant. And I'm going to tell you what the order of the reactant means in just a few minutes here. But that's how you would format it, that's how you would write it. Now, how do we determine and figure out these order of reactants? Okay, we're going to study it from the reactant perspective, caring about that because really studying it under the conditions of initial rate method, where you're really just looking at the reactants, you're not really caring about the products, and they're designed to minimize that variable of a reversible reaction if it does have an equilibrium position. So we're really looking at the reactants here. And they collect the data at the beginning of the reaction where you're at time equals 0 and you have an initial concentration to begin with. It's called the initial rate method. All right. To determine your order of reactant, you have to look at experimental data. And what they're going to give you is a series of concentrations, initially with a series of rates. And you'll see a problem like this towards the end of the notes. That's what we're going to focus on for part 1, is looking at how to figure out the order of the reactants from the experimental data. Part 3, we'll look at it, how to figure out it from the proposed mechanisms. So that's going to come. There is a way to do that. I just want to make sure that everybody understands you don't look at the balanced reaction here. We always looked at the balanced reaction for equilibrium to figure out the exponents. Well, that is not what you do here for kinetics. Those exponents are not based off of the balanced reaction. They are completely based off of experimental data that is given to you. So that's one thing I wanted to make sure that we're very clear on. Here we're not comparing the powers to the coefficients in the balanced reaction for the rate laws. Now, reactant order and overall reaction order. The previous example we showed you one with the nitrogen dioxide where we only have the one reactant. This is giving you a generic example if you had 2 reactants in the rate law, reactant A and reactant B. Now reactant A is going to have its own order of reactant. Reactant B is also going to have its own order of reactant. So you'll see it referenced that way. They'll hone in on the specific reactant. And then they could also ask you about the overall. The overall is very easy to find. All you do is add them up. So N plus M, that gives you the overall for the reaction. Most of the time, though, they will specifically ask you about a reactant. I don't see a whole lot of overall asking, but sometimes they do. So for this particular one, we have the rate equals rate constant K times the concentration of A to its order of reactant, concentration of B to its order of reactant. Now, I do also want to say something about the rate constant. I do not like this, but this is how it is. The rate constant is always noted as a lowercase k, which is very confusing because we have to deal with equilibrium k, which is an uppercase k. Don't let that confuse you. Lowercase k, rate law. Keep those separated in your head. I know, they really like the letter K. I agree. What is up with chem people and the letter K? Very good point. I like that. But don't get it confused. Don't get it confused with equilibrium K. Equilibrium K is a large uppercase K. I know, it's a good letter, right? I just work here. They chose these letters way before I was born. I can just tell you that. All right. Here is an example. So we wanted to calculate or look at, what are we looking at here? We want to know the overall for this one, right? Very simple. The order of reactant for A is 2 or second order. The order of reactant for B is first order or 1. So we add the 2 and the 1 together. I know this is rocket science. Wow. It's a third order reaction overall. So the reaction order for the entire thing would be third order. Well, we're about to find out about the orders. Let's talk about those orders. All right. This is how they figure out the order of reactant when we're using experimental data. Method of initial rates. Told you, initial rate method. Value of the initial rate is determined for each experiment, the same value of T as close to 0 as you can get. So right at the beginning of we know it goes fastest at the beginning anyways, right? So this is where it's going to be measured. Several experiments are carried out using different initial concentrations. They vary the concentrations between the different reactants, so then we can calculate it. All right? The initial rate is determined for each run, and they create a nice experimental data table for you. The results are then compared to see how the initial rate depends on the initial concentrations. So we do a mathematical analysis of the data, and I'll show you how to do that, and we'll be able to tell the order of the reactants. But before we do the calculating and figuring those out, let's know what they actually mean in terms of rate. If you have a 0 order reactant, this is what it means. It means you can change the concentration all you want. You can double it, triple it, quadruple it. It is not going to change the rate. The rate stays the same. So we designate this one. We call this one 0 order is no change. You can do anything you want to the concentration. You will not change the rate. It stays the same. It just is for certain reactions. This is how it works. Doesn't matter. You do not need to include these in the rate law. And let's think about that, because anything to the 0 power is going to be 1. So why do we bother writing in it there? Because we're really just going to multiply by 1. So there is no need to do that. So basically, if you're looking at, data here, say you've got concentration of A and that equals 0.1 molar, and that's 1 molar per second in terms of the rate. And we decide to quadruple our molarity here. Guess what? The rate still is 1 molar per second. It does not change. 0 order ones are boring in my opinion because they don't do much. Let's talk about first order. You double the concentration, you double the rate. This one we call same change. Same change. So if I triple the concentration, guess what happens to my rate? It also triples, exactly right. Okay? So whatever you do to the concentration, that is how the rate would be affected. Oops, sorry. So for instance, we have our A, and we have our 1 molar, and it's 1 molar per second. And I decided to quadruple the concentration. Guess what? My rate also quadruples, like so. First order, same change. And second order. You double the concentration, the rate is going to quadruple. So this is known as square of the change. So whatever you do to the concentration is going to square that number factor for the rate. Square of the change. So if you triple the concentration, the rate will be multiplied by 9. So simply going from A equals 0.1 molar, and that's 1 molar per second, just for easy numbers. If I make the concentration of A now 0.3 molar, which is triple, that means this would be 9 molar per second, like so. So 0 is no change, first order is same change, and second order is square of the change for the rate and your manipulations with the concentrations. So let's do some practice here with those ideas. What is the rate law for this particular reaction shown above, where we have A plus B plus C gives you CD there at the top? It tells me that we have A being first order, B is second order, and C is 0 order reactants. Now, how would we write out our rate law for that? We have rate equals our small constant K. That part never changes. Its rate equals the rate constant K. The first one, A is first order. So I'm just going to write in that. You don't really need to put the power of 1 there because it's an understood one for it being there. I mean, I suppose if you really want to do that, you could put a 1 there, but it's not necessary. The B is second order. So we would write in here the concentration of B squared, because that's second order reactant. And then it says up here that C is 0 order. So let's go back and think about this. If that is 0 order, C to the 0 order, that is always going to equal 1. We don't need to write it in there. It's just extra stuff. Doesn't change anything, so let's not write that in there. Now, looking at our rate law and realizing what we know about our reactants, what will happen to the rate if you quadruple the concentration of A? Good. 4 times our concentration of A means, yes, we're going to get 4 times our rate. Very good. Now let's look at the next one. That's because, of course, A is first order, so that's same change, right? Same change. What will happen if you cut the concentration of B by half? 1/2 of our concentration of B. What happens there? What type of order reactant is B? It's second order, right? So that means square of the change, right? So 1/2 of B is going to be 1/2 squared of the rate, right? So yes, it's 1/4 times the rate here. Very good. Exactly right. Let's take a look at some more. What happens if A and B are both doubled? So we're going to double A and double B. So what does that mean in terms of our rate? Doubling A here, what does that do to our rate? Doubles the rate, okay. What about doubling B here? Quadruples, or square of the change like so. So that's going to be 2 times 2 times 2, which is 8 times the rate. There is a 1 for 8, whatever.
It's like doubles, triples, quadruples.
Yes, I don't know anything past quadruples though.
Yeah. Is there something past that? Do they have a word for it?
I'm sure there is a word out there. I don't know.
Pentuples?
Pentuples? Yeah, that's a good question. So what happens if C is increased by a factor of 10? Nothing. Very good. C is 0 order. This is 0 order. So this is a no change. Nothing. No change to our rate. No change because it's 0 order. How about what will happen if A is quadrupled and B is cut in half? 4 times A and 1/2 times the B. What are we going to see here? Well, this would be 4 times for A. And here this would be 1/2 squared for the B, which yes means we're going to get 4 times 1/4, which means 1 times the rate, which is really no change. Very good. Make sense? Yes, no, maybe so? They do. They cancel each other out, basically. That's a good point. They do cross out. Alrighty. Now on to the fun one where we get to work with the data. Exercise 2. For the reaction. Our reaction involves the bromate ion. We have bromate plus bromide plus hydrogen, giving us liquid bromine and water. All right, back up here, we've got bromate plus bromide plus hydrogen, giving us bromine liquid and water. This is our overall reaction. They gave us the general form of our rate law here. The bromate, the bromide, and the hydrogen there. We don't know the order of the reactants. That's why it's N, M, and P right now. We don't know them. We're going to figure them out from the data. Okay? So have the general one out there for you. And now we're going to look at our data table, which is on your sheet there. This is done through the method of initial rates, the initial rate method. Okay, they'll give you a data table like this, where they show you the concentrations of the different reactants, bromate, bromide, hydrogen. This is experiment 1. This is experiment 2. This is experiment 3. And this was experiment 4 that they run. And what you can see with all of the different concentrations is they're different depending on the experiment. They also provide you the rate over here for each individual experiment. And for the differential rate law problems, this is the kind of thing you're going to see. And it doesn't change much from this. You're going to see these data tables with these initial concentrations and their rates that have been calculated. So what you have to do here to figure out the individual orders of each reactant is you need to look at 2 experiments. And you pick your 2 experiments based off of the one you want to calculate. Like for instance, for bromate, I need to pick 2 experiments where bromate is the only concentration that's changing. So I want bromide and hydrogen to be the same. So if I'm looking at that up there where there aren't any changes in the bromide or the hydrogen, which 2 experiments would I pick?
1 and 2.
I would want to pick 1 and 2, exactly right. Now, 1 and 2, that's what I'm going to pick for my bromate here. So I'm going to write this whole thing out just to show you what it means, but then we're going to shorten it for the other 2. Now, I always put the one that has the higher concentration on top. It's just easier calculating wise. So I'm going to put experiment 2 on the top because it's 0.2 and this is 0.1. Now, of course, this is representing the rate part of the rate law. Okay, remember the rate law is going to be the bromate here times the bromide times the hydrogen. We're going to use the experiments and the rate law, the generalized rate law, to figure this out. So now, okay, this is going to be K over K for each experiment. The concentration of the bromate for the experiment 2 was 0.20 molar, right? And it is raised to some power. We don't know what the power is because we don't know the order of the reactant. Experiment 1, though, the concentration was 1, raised to that power of the order of the reactant, which we don't know. Now, these two. This would go in here like this to represent our bromide, like so. And here, I'll use blue for this one. This would be for the hydrogen. And that's supposed to be a P. So this is what I'm showing you. Basically, we're using the rate law to figure it out. And as you notice, do I really need to include the bromide and the hydrogen in here? Because what are they going to do? These are just going to cancel, so we really don't need to include those in our calculations. But now I can enter the numbers for the experiment here, the rate part. So we have 1.6 times 10 to the minus 3 over 8 times 10 to the minus 4 equals K over K, which those also cancel, so you don't really need to include them. That's going to be the 2 over the 1. So basically, and try to do this without the calculator. Let me show you why. They can put this in multiple choice, because if we move this over 1, this becomes minus 4. So really, it's just 16 divided by 8, right? That's a mental math using your exponent math that you know. 16 over 8 means we're going to have 2 equals, what's 0.2 over 0.1? 2 raised to the raised to a power, right? So what is the power then? So the order of the reactant is going to be 1 here. The order of the reactant for the bromate happens to be 1. So we know this one happens to be now just a 1, like so, if we're starting to fill in our rate law. Now, let's go ahead and look at bromide. Let's look at bromide. What two experiments do I want to do to find the bromide? Or what two could I use? Where bromide is changing, but the other ones are not. Two and three sounds good to me. So that's what I'm going to do. Use my experiment 2, experiment 3. These stay at 0.2, these stay at 0.1. So now I'm just dealing with, so I would do 3 times 10 to the minus 3 over 1.6, 10 to the minus 3. That's going to be equal to 0.2 raised to the m, 0.1 raised to the m. This is why we're shortening it down, where we don't have to put all the other stuff that cancels in there. Now, that means, what is 32 divided by 16? Because they're basically the same exponents here. 3.2 divided by 1.6. That's going to be 2. So this equals 2 equals 2 to the m. So what is going to be the order of reactant for our bromide? That's also going to be m equals 1. So the bromide is just going to be to the first as well. Now let's look at the hydrogen. Finish this up here. What two experiments do I want to use for my hydrogen, where the other two are not changing? One and four? 1 and 4 looks good to me. All right, so we have for 1 and 4. So I'm going to put 4 on top and 1 on the bottom. 3.2 times 10 to the minus 3 over 8 times 10 to the minus 4. That's going to be 0.2 raised to the p, 0.1 raised to the p. Now once again, if I move this over 1 to the right, this becomes minus 4. So really that's 32 divided by 8. So what is 32 divided by 8? 4. So now we have 4 equals 0.2 divided by 0.1, 2 to the p. So what is p going to be? P is second order. Good. So down here for hydrogen, this would be second order. And this is how you would figure out the rate law for our lovely, for this particular problem. This is the rate law. So given the data, can we determine the order of reactants? Now, there's one other thing we need to calculate. It says determine the rate law and the constant K using the information. How could we find K? What could we do? Never mind, we will figure out K next time. Have a good weekend.
See.